Hello everyone, this is lecture 2 of course PE 645. In the previous lecture, we have covered the meaning of artificial intelligence and the sub-branches such as machine learning and deep learning, and the meaning of radiomics, and then we covered multiple modalities such as CT, MRI, and PET scans, and finally we covered a radiomics workflow or the standard workflow of a radiomics project using artificial intelligence, and we mentioned that it consists of 6 steps or more, and we are going to follow the standard 6 steps of the radiomics workflow, which are getting the dataset, applying manual segmentation, and optionally apply automatic segmentation, and then extract the different radiomics features from these ROIs or region of interest, and then apply pre-processing such as feature selection, where we get the most significant radiomics features. After that, we start developing the artificial intelligence model for the prediction or classification, and in that step, we apply training, validation, and testing, and then report the performance metrics for the training, validation, and testing. And we mentioned the meaning behind each subset, and we also covered the meaning of overfitting, underfitting, and by the end of that lecture, we mentioned that we need to report a high-performance system and explainable model, and explainability here means we need to explain the decision of the model, why that model produced that decision. For example, why that system produced that there is a cancer here or a tumor there, and so on. And to make an efficient model, we mentioned that we need a high-performance model and explainable one. Through the lectures, we are going to cover the 6 steps in details, starting from the dataset until we reach an explainable model. So let's begin. We covered different modalities, as we mentioned, CT, MRI, and ultrasound, and in each of them we can retrieve images or videos. A video is a set of images or a set of frames. So the main concept here is an image or a frame. An image here is a digital representation of a visual scene, object, or a graphic, and an image consists of pixels arranged in a grid. And a grid here means we have something like a table, where each pixel or a cell in that grid contains color and intensity information. So let's look at this image. It consists of pixels arranged together like a grid or a table, like that, and in each of them there is coordinates like x and y, x position and y position, and the pixel value or the intensity value. The intensity here means the color of the pixel or the grid of the pixel, for example 125 or 255, and the range of the intensity in each pixel ranges from 0 to 255 because we are dealing with pixels in a range of 8 bits. So an 8-bit pixel means that we have a lower value of 0 until we reach a higher value of 2 raised to the power of 8 minus 1. So the maximum value that can be accepted or reached by the pixel is 255. 0 means a darker or a black region, and 255 means white or brighter region. So a value of 127 means a mid value between a black and white, which looks like a grayish pixel. So if you look at that image, then you will determine that all of these values are closely to 0. And if you look to that image, all of these values are close to white, which is 255. And other pixels are in the range between 0 to 255. What we are dealing here is called a gray image. So a gray image consists of pixels, and each pixel has a single value from 0 to 255. There is another type of images called RGB images or color images, where each pixel has 3 values: R for red, G for green, P for blue. Now we have an image. We mentioned that we need to apply segmentation, and the segmentation here, as we mentioned, is something that aims to delineate or applying a contour or a bounding box around the region of interest. And mostly a mask is a binary or a grayscale image. And the difference between a binary and a grayscale image, grayscale, we mentioned it earlier, it consists of pixels. Each pixel has a value from 0 to 55. while a binary image also consists of pixels, but here each pixel, whether it's black or white, whether it's 0 or 255, like what you are seeing here, 0 or 1. 0, it's black, 1, which is reflected by 255 as a value, which is white. And we use the binary image or the grayscale image for masks to delineate or put contours around the region that we are interested in to capture it in further processing. So the areas that we need are put in white or highlighted in white, and others are in black. And we will know later the benefit of doing that. Now we have an image, we have a mask. We will do something or an operation between these two images to produce the ROI. But let's understand the meaning of the ROI. We mentioned it's a region of interest, or the region that we need to process it or apply analysis on it. So an ROI is a portion of an image which is selected based on the mask for further processing, analysis, and manipulation. So the ROI is the product or the output of a specific operation applied between the image and the mask. And the mask here is retrieved by a physician or an expert in the field by getting the image and applying manual segmentation using any software such as Adobe Photoshop or any available software to get the mask. So let's assume now we have a dataset that consists of images and masks, and we need to understand the process or the analysis to get that ROI. To do that, we can apply a bitwise AND. So the specific process here is called bitwise AND. So if you get the image, apply bitwise AND between it and the mask, you will get the ROI. So how this function, which is called bitwise AND, operates. Let's assume we have a pixel here, and we have the corresponding pixel in the mask, which is 1 in this case, or white, or 255. Simply, the bitwise AND allows the transfer of any pixel values in the white region or in the ones region. Why? Let's assume, as we mentioned, it's 1. Multiply it by a pixel value, then the result will be the same pixel value. But if it's black here, so then this value will be 0. So 0 multiplied by any value will be 0. So the bitwise AND here, and the benefit of using binary mask that consists of ones and zeros, or whites and blacks, is to filter only the region covered by white pixels in the mask. So the concept here is simple. If you have an image and a mask, apply bitwise AND between each of them together to get the region of interest. A second point here, if you look at the ROI, you will find that there is a large space that contains black pixels, which is useless in our processing. And we need to get rid of these pixels or the surrounding region around the ROI. How to do that? Simply find something called a bounding box. And a bounding box is essential to find only the region of interest or the organ that we need and get eliminate of the surrounding black regions, which is a result of the bitwise AND operation. Simply, the bounding box operation tries to find a rectangle that surrounds the region, and the result of it is finding the XY coordinates, which is the top left corner, which is here, and width and height. By finding these 4 values, we can obtain and extract only the organ, which in this case is the liver. So our aim is to apply bitwise AND between the image and mask to get the ROI, and then apply a bounding box to get rid of the surrounding black pixels or regions to get a cropped ROI. If you applied that on the different images, now we will obtain the cropped ROI for these different images. Further steps will include getting these cropped ROIs and extract the different features from them. So how to code that using Python? In the first code, which is called image manipulation, you will find the implementation of applying the bitwise AND and the bounding box to get the final output, which is here. So let's understand the different steps in it. First, we are importing the libraries or packages which is used by Python. The first is CV2, which is OpenCV, which is necessary for image processing, such as reading and writing images. And the second is used for displaying and plotting images, is called matplotlib. Then we define the paths of the images. Here we have two sample images. One is called sample liver image, which is this image, and sample liver segmentation, which is the corresponding mask, which is here. Next, we will read these two images, and as we know, we are dealing with grayscale images, because if you own each of them, there are no colors. So let's read them in the grayscale mode by using the CV2 package, which is OpenCV, as we mentioned. There is a function called mread or imageRead. We pass here the path of the image or the mask and the type or the mode, which is grayscale. Then we will store it in two variables, one for the image and one for the segmented mask. And here it's an optional step by getting the shapes of the two images and printing them on the console or the command window. And this step can benefit you by ensuring that the two images have the same shapes or dimensions. Then there is a function which is built already in CV2, is called bitwise AND. It accepts the image and the mask and result in the ROI, which is the region of interest. Another optional step is to write or save the ROI on your hard disk. For example, it will look like that after saving it. And this step can benefit you later if you have multiple images and you need to extract these images individually to apply further processing, such as classification or feature extraction on them. After getting the ROI, we mentioned that we need to apply the bounding rect and get the different values, x, y, width, and height. Here, there is another function, is called bounding rect, that accepts the ROI and result in x, y, w, and h, which are x, y are the top left corner coordinates, width, and height. And to get the cropped version, which is that image, simply we will apply image cropping, which is defined in image processing. Simply we have x and y. So the starting point to get the cropped version is to define the starting x coordinates and the ending x coordinates, and the same for y. Y, which is the starting point, and here is the ending point. How to get them? Simply, this is x, and this is x plus width. Here, this is y, and this point is y plus h. So, if we told the application or the program to get only the region which is bounded by these 4 points, then the cropped version will be retrieved. So here, we told that we need from y to y plus h in the height vertically, and x to x plus width horizontally. And we started by the vertical coordinates here, or the vertical dimensions here, because OpenCV deals with y coordinates first and then x coordinates, or deals with heights and then width. By doing that, we will get the cropped version. To plot a figure that looks like that one in the slide, simply we need to plot the 4 subplots together: image, mask, ROI, and the cropped version. So this package, which is called matplotlib, will help us to do that. First, create a figure and define the dimensions or the size of that figure, and start to fill it with the 4 subplots. The first subplot hits here, the second, the third, and fourth. In each subplot, we defined the position of it. This means we need one row with 4 columns and start to fill the first position. Here is the second position, here is the third position, and so on. Then there's a function called mShow. We define here the image that we need to display and the color map of it, which is gray. We can put a title and remove the axis. And removal the axis here is simply hide the axis. So instead of putting numeric values here from 0 to 55 along the axis, we need to get rid of it by simply adding plot.axis off. Then tight layout to adjust the spacing between the subplots. We will do the same, but with different images. Here for segmentation in the second position, here for the ROI in the third position, here for the group in the fourth position. And finally, we can store the figure using save figure function by defining the path of storage, the resolution, and here is an optional step to also adjust the layout and the spacing around the figure. Then we can use the function show to display the figure, and to clear it from the memory, we can use these two steps. So now we understand the meaning of an image, the meaning of a mask, and the ROI. We understood that by applying bitwise and between the image and the segmentation of the mask, we can get the ROI. And to get rid of the surrounding black region, which is useless, we can apply the bounding rig to get XY width and height, and based on these four values, we can apply grouping on the ROI to get the group version of that ROI. We did that on an image. What about a volume? Simply a volume here means multiple images or multiple frames. There are a common type in radiomics and the medical field is called NII volumes, and they are 3D medical imaging datasets which are stored in that format, NIfTI, and this format is commonly used with MRI and CT scans. It stores the volumetric data, such as what you are seeing here, with the embedded metadata, such as patient information, voxel dimensions, and orientation, and the storage of it requires a special software that supports opening this format. To know that this file is an NI file, then simply you will find that extension. So if you find a volume that ends with .nii, then this means this is an NI volume which is extracted with MRI or CT scan, for example, and contains 3D volume, which consists of multiple frames or multiple images. So if you have one volume for a specific patient, let's assume these are 10 images, then you will require that the doctor or the physician or the expert will make 10 segmentations, one for each image. So we have images volume, then you will have masks volume. The first frame has a corresponding mask, second frame has another corresponding mask, and so on. There are many other formats that are used in medical imaging. We mentioned one of them, and we need to do the same process on that volume. So instead of applying bitwise and bounding box on a single image, we need to apply that on the whole volume. Simply extract the different images from the NII to images, and the same for the mask. After that, get each image and its corresponding mask, apply bitwise and then the bounding box, and extract the cropped version of that ROI. Do the same for other images in the volume. You will retrieve at final a cropped version of the ROI for the whole volume. So the first step is to read the NII and extract from them the different slices or images. There is a code here called NII 3D files. Here we imported CV2 for image processing, OS, which is a built-in function in Python for the different files operations, and we imported NumPy package for the numerical operations, and NIPabl to handle the NII files. We defined the paths for the volumes, one for the images or the volume and the corresponding segmentation volume. Then we defined the storage paths, one to store the slices for the volume and another for the segmentation frames. We use the function here called load, and here to load the volume and here to load the segmentation frames. To extract the data, as we mentioned, we have data and the metadata. To extract only the data, we can use the function getIfData. And here we have the volume data, and here the corresponding segmentation data. Also, this is an optional step to ensure that the sizes are the same for the volume and the corresponding segmentation volumes. Then we inform the script to create the storage folders if they don't exist. So initially we don't have these folders, whether you create them manually or let the script to create them on behalf of you. Then we will start to extract one frame by another. To start extracting the different images from the volume, we need to know how many images do we have. So if we got that number, we can apply a loop to iterate from the first frame or the first image until the end. So simply in the volume, we can get the shape, and based on that shape, we can get the dimensions of each image and the number of images. Simply, if you find a number like that, 512, 512, and 100, then this means that each image has a shape of 512 by 512 as a width and height, and the depth, which is the number of images, is 100. So we can get the shape of the volume, and we need only the number of images. We have 3 values, but we need only that value. So simply, this is called a tuple, similar to lists and vectors. We can get that value by simply indexing it. Python, as many other languages, start from index 0. So the first element, which is 512, starts by index 0. The second starts by index 1. So this value has an index of 2. So if we got the shape and we asked it to get the third element with an index 2, then we have the number of images in that volume. And that's what we did here. We have the shape and index of 2 to get the third dimension, which is the depth or the number of slices. Then we use it in a function called range in a loop. So the counter starts from 0 until it reaches that number minus 1. And this is the aim of that function, which is called range. It generates a sequence from 0 to the end, for example, 0, 1, 2, 3, and so on. And each iteration will store the new number in a variable called I. So in the first iteration, it will be 0, the second will be 1, and so on. Here, we extracted the slice and the corresponding mask. How we did that? Simply using the colon. And here we mentioned that we need all of the pixels vertically, all of the pixels horizontally, but at slice I. So if it's 0, it will get the first slice. If it's 1, it's the second slice, and so on. The same for the segmentation. We have the volume, we have the segmentation, slices. Then we can write both of them together in the corresponding folders. Here we stored the volume in the volume folder and the segmentation in the segmentation folder. If you executed the code, you will get 2 folders. Here we have the volumes, the volume slices, and here we have the segmentation slices. Now let's understand the 2 steps that we skipped. Let's start by this one. This step means that we are telling the code to modify the content of the segmentation slice. Why? Simply because this volume contains 2 segmentations, one for the organ, the whole organ, and another for the tumor. Both of them are stored together in the same image. So the person who applies segmentation on each slice segmented only the organ and also segmented the tumor. And to distinguish between each of them, they gave each of them different values or labels. They gave the whole organ a label of 1 and the tumor a label of 2. And of course, the background is 0. So now we have 2 labels. And for sure, not all of the datasets is like that. It depends on who is segmenting and the way they are segmenting the images. Simply, you can find images and masks with 3 labels, 4 labels, and so on. For our task here, we have 2 labels, one for the tumor and another for the whole organ. So if we need to focus only on the organ, then we need to ignore the tumor. And if we need to focus only on the tumor, we need to ignore the organ. How can we do that? By manipulating and modifying the mask values. So if you need to display both of them together, give them 2 different gray values. So here I am telling the image that for all of the labels that contain the value 1, replace it with 127, which is this grayish value. And for the labels with 2, apply 255, which is white. And in this case, if you need to display both of them visually in front of you. But if you need only the organ, simply give all labels 1 or 2 with a value 255. So the organ which contains the tumor, will be filled with white. But in the case, if you need only the tumor, then you need to ignore the organ. So, for the organ, set it with 0, while for the tumor label, set it with 255. So if you need only to extract the features from the tumor, you will use that approach. If you need to apply processing on the organ, then you will use that approach. And here, what we did. What about this step? By default, without any rotation and without this step, you will find the images in that direction. If you found something like that, which is not visually preferable, then you can rotate them by 90 degrees using the function rot or rotate 90. You will pass the slice and get the slice after rotation, and the same for the segmentation. But if you did that on a different dataset and from the beginning you found the image is aligned and rotated and visually preferable, then you can comment this step and ignore it. Now we know how to deal with images, how to deal with volumes, and the meaning of different steps behind each of them. If you remember, the next step after getting the dataset and applying manual segmentation to get the cropped ROIs or the region of interests is to apply handcrafted features. And it's worth noting that there is another approach called automatic feature extraction. The difference between handcrafted features and automatic feature extraction is that handcrafted features are extracted known features which are retrieved based on mathematical operations or statistical operations, while automatic feature extraction involves getting a model that learns the different patterns from the images and extracted numeric values or numeric features. For handcrafted features, you can use that approach if there is no visual differences between the tumor types or the different categories. For example, you can two tumor types, one that looks like that and another looks like that. So if you applied automatic handcrafted features in that approach, then it may not be able to discriminate between each of them to get the correct features. But if you got enough data and it's easily or visually easy to discriminate between the different categories or the classes in your dataset, then you can simply apply automatic feature extraction. The benefit of handcrafted features is that you know what you are extracting. Simply, the standard deviation. You understand the meaning behind it. But in automatic feature extraction, you have a value. And you cannot explain the meaning behind that value because you are simply dealing with a black box. You are inserting the image or the cropped version and getting a numeric record. You don't know the meaning behind each value in that record. But here in handcrafted features, you understand well the meaning behind each value.